Hello everyone, my name is Junho. I'm going to present Action2Score, an embedding approach to score player action. MOBA is a game genre representing team competition strategy game, where two teams face off to destroy each other's base. Most MOBA games have a ranked system that groups players at a similar proficiency level. A player's rank is determined by matchmaking rating, MMR. MMR increases when the player's team wins a match and decreases when it loses. It is reasonable that a player's MMR depends on the game results in the team playing games. However, it sometimes can be unfair. For example, some free riders piggyback on teammates without their efforts. On the other hand, some players show heroic performances even their team is losing. Therefore, game communities use metrics such as KDA to evaluate players' individual performance. However, those metrics use only end-state statistics, so we cannot assess respective actions' contributions. Also, with those metrics, some players can be underestimated. So we wanted to design a model that converts a player's action into a score representing how much the action contributed to the team's achievement. Also, we focused on the causal relationships between the player's action. Imagine a situation where a player has bought an item and then killed an enemy champion. Killing an enemy is usually considered beneficial for winning a match. Then the act of buying can be assumed to be likely beneficial. Therefore, we use the GRU, one of the RNN structures, to reflect the causal relationships. Moreover, we implemented our model to take players' action in a time-reversed sequence to estimate the cause action through the result action. RNN structure is combined with a single layered perceptrons, and it takes a sequence of players' action and then outputs scores for corresponding actions. Also, our model consists of two main parts. The left part is a GRU SLP part, which comprises GRU SLP models that I explained previously, taking each player's action sequence of a match. The right part is the discernment and evaluation part. DP discerns the winner by comparing it to team's total score and calculate the loss to execute backpropagation. We designed two discernment method loss function pair for DP. In the confidence cross-entropy loss pair, DP calculates how confident the team given a higher score is the actual winner. The equation below depicts how DP computes the confidence and loss values. On the other hand, DP does not compute confidence in the other pair. Also, we use the ReLU function as the loss function, so the loss to be zero unless the discernment is incorrect, regardless of the score gap. To conduct an experiment, we collected more than 240,000 League of Legends match data using Riot API. We used the 200,000 of matches for training and validation, and the rest of data was used to build a test set. From the match data, we set up 6 features. Timestamp is the time point at which the event occurred. Champion is a character chosen by a player. Lane is a chosen lane of the player. Position is the player's location on the map when the event occurs. Event is the type of events such as champion kill and its weight. Distance depicts how much the player is isolated from their teammates. For the experiment, we created 7 models to compare performance. Because of time limitation, I will focus on the performance of the main model. This table displays the discernment accuracy of the model, comparing 3 baselines. Our model discerns the winner much more accurately than using common metrics. Meanwhile, our model had to give similar scores to the actions in a similar context, regardless the players of action is the winner or not. This figure shows the score distributions according to the action feature vector. The dimension depth of the feature vector was reduced to 1 using PCA. The action with the similar feature vector can be considered to have similar worthiness in a match context. We can see that our model gives similar scores to the actions with similar feature vector. These figures display the relationship between players' ranking according to model scores and common metrics. It shows some positive correlation between the model score and the common metrics that depicts that our model properly reflects individual performance evaluation by common metrics. These figures display the number of overestimated players by lane according to common metrics. The graph shows many players can be overestimated when using common metrics. Lastly, I will show the visions of our model. The experimental results show that our model has more advantages than common metrics such as KDA in evaluating the individual performance of a player. We expect that MOBA games can use our model to adjust the changing amount of MMR according to the match outcome to overcome the limitations of the current MMR system. Or they can simply display scores on the leaderboard to praise players. Furthermore, although we designed our model to fit League of Legends, the fundamental structure of our model has enough generality, so the model can be used for other games, including MOBA game like Dota, and different genres such as first-person shooter game, with only minor adjustments. Thank you for listening.